something called redox reactions, okay? And redox stands for reduction and oxidation reactions, okay? So redox reactions are when we have electrons that are transferred during the reaction. So not just protons that are transferred like an acid-base, but electrons that are transferred. And so this is when elements or compounds go from one oxidation state to another, okay, during the chemical reaction. They rebond with something else, or they form something new that causes them to have a different oxidation state. Okay, so we'll review a little bit what oxidation states are. This is an example of sodium and chlorine and their reaction to form salt. Right, we take individual sodium atoms and individual chlorine molecules and we rearrange them, right, to now form sodium chloride. And within that sodium chloride, it is now an ionic molecule, which means there's been a change of electrons. We take two neutral molecules, we ionize them, and now form an ionic molecule. So there's been a transfer of electrons that happened during that point. Okay, so this is an example of a redox reaction. So we're going to go through real quickly the rules for assigning oxidation numbers. We did this in Chem 1, kind of briefly, but these are ones this time you'll have to memorize. Okay, so I don't think you had to memorize them in Chem 1. You will have to have them memorized for this one, but they're pretty simple. Okay, and why don't you grab your periodic table out if you don't have it out yet, because most of the time it kind of follows the charges, but we'll go with that. Okay.
We need to memorize it for this next test.
Yeah, that'll be on the test. Yep. Okay, we'll go over it again, but it's pretty simple. Okay, so oxidation states, first thing we need to know about oxidation states is they're like pseudo charges, right? They're not full on charges, but they're kind of charges, right? They're how atoms kind of are representing their electrons, or how their electrons are arranged. So we think of them as charges, but they're not full on charges, okay? So the oxidation state of an atom in an element by itself is 0. Okay, or any elemental type molecule would have an oxidation state of 0. So this would mean if we had the molecule H2, hydrogen would just have an oxidation state of 0. Okay, I list oxidation states up above the atom. I don't know that that's a hard and fast rule, but that's where I tend to list them. And then I use down below that as my workspace. We kind of talked about this last year. We make the little square for oxidation numbers. We show the work that way, but generally I assign oxidation states up at the top. But this is an elemental atom, or if you had something that was just sulfur, right? Sulfur would have an oxidation state of 0. Any element by itself has an oxidation state of 0. Okay? If the monatomic ion has a charge, or if you have a monatomic ion, then the oxidation state becomes the charge of the ion. So that means if I have an element with a charge, H plus, now the oxidation state is not 0, it's +1, right? It's the same as the charge. It's showing the electron configuration or electron arrangement around that atom.
So why for something like phosphorus, where it has a charge of negative whatever,
3
3 to start out with, would it have a -3 oxidation state?
Yep.
Okay.
Yep. Phosphorus is -3. Same as the charge. If it's given a charge in the chemical reaction, right? We're going to look at this in the scope of chemical reaction. So as your chemical reaction goes, it would be rare that we'd see an ion bond with something, right? It's usually a double displacement or a displacement reaction. But if it has a charge, then yes, the oxidation state is the same as the charge.
Wait, so what's the difference of seeing an elemental atom and a monatomic?
Okay, this is monatomic ion means it has a charge. Elemental atom would be like H2.
Oh, okay.
Right, so that's a molecule by itself, no charge. Right, ion has a charge. H2 is a neutral molecule.
So, like, what would H2 look?
Each hydrogen would have an oxidation state of 0 in that case. What'd you say?
And what would it look?
This is just the 0 oxidation state. I just listed it up above. But what do you mean O?
She meant for H2O.
I'm sorry. Okay, we're going to go into the rules for that. But H2O in water. Oxygen's a -2. -2. Each hydrogen is a +1. Okay, but we'll get to how that rule applies here in just a second.
So would that be like n-3 versus just like...
Just N, right? N by itself would be 0. And -3 would be -3.
Okay.
Yep. Okay, so here's where we get into what I call the big 3. There's big 3 elements that kind of take precedence when we're looking at oxidation number assignments. Fluorine, oxygen, and hydrogen in that order. Fluorine maxes out everybody and gets always the predominant oxidation state. Why? What's special about fluorine?
It very reactive.
Yes.
In the
Why? No, yeah. Yep. We're on the right track.
It just needs one more to.
Yes. Yes. It's got a term for it. It's the most. Most electronegative. There we go. Most electronegative atom we have. And it's the most electronegative, which means it wants to take electrons from anything and everything. Because you guys were right. It's got 7 valence electrons. And those 7 valence electrons are closest to its nucleus. Right? It's got, in its closest outer shell, a vacant spot. The farther you get down on the periodic table, iodine still has 7 valence electrons, but they're so far removed from the nucleus that it's not as important that they receive that 8th electron. Does that make sense? So fluorine takes precedence. Its oxidation state or oxidation number, always -1, no matter what it's bonded with, -1. Okay? Second of the big 3 is oxygen. It has a -2 oxidation state. Anytime it's in a covalent compound.
I just had a question when you said about the periodic table. The farther down you get, the farther the things get away.
That's right. Right.
And so like hydrogen is like really close.
Right.
Okay.
Right.
Okay.
Okay, so that's okay. Oxygen always gets a -2 oxidation state when it is in a covalent compound, except in a peroxide, which we don't see that often. Peroxide would be like if it's like H2O2 is a hydrogen peroxide. So peroxide means it's like an O2 bonded with something, not something we see super often. Okay. If oxygen is bonded with a metal, same type of thing. It almost, when it becomes a metal and a non-metal bond, then it's an ionic compound. And so really you just look at their regular charges, right? Because it's ionic, but -2. Okay, so fluorine -1, oxygen -2, and then hydrogen is the last of the big 3. It's going to have a +1 oxidation state in covalent compounds. Okay, +1 oxidation state. So let's figure out how we're going to form all the different oxidation states. The sum of our totals have to add up to 0. Some of our totals have to add up to 0. So I'm going to show this in an example here pretty soon. That's if our compound is neutral. So I maybe want you to write in where it says right here in neutral compounds. Okay? Neutral compounds. Did I write out these oxidation states for you, or are you writing them in? Or is it like fill in the blank?
They're written out.
They're kind of written out for you. Okay. Go ahead and add in their neutral compounds. Okay? Because if we have ions, then the sum of our oxidation states have to equal whatever that charge is on the ion. Okay, so if it's neutral, we want our sums to add up to 0. If it has a charge, we are going to add them up to that charge, whatever the charge is. Okay, so let's do a couple examples before we switch to the next slide here. But we're going to look at following kind of a pattern here. We always assign the oxidation state to the element on the right first. The most electronegative element gets to assign its oxidation state first. Okay, so let's say we have, I don't know, CO2. Okay, carbon dioxide. When I find the oxidation states, I first look at the compound and say, does this compound have a charge? Yes or no? No. If I had a charge, it would be listed up there.
Oh.
Right? No charge. Which means I want my totals down here on the bottom to add up to 0. I use this just below here space as like a workspace. Right? It doesn't have anything to do with the answer necessarily. It just allows me some room to work. So I want the totals to add up to 0. Second thing I'm looking for is, does the compound contain one of my big 3?
Yes.
Right? Fluorine, oxygen, and hydrogen are my big 3. So yes, it does. So it takes precedent. Oxygen each gets a -2. And how many oxygens do I have? 2. So I multiply on the way down. -2 times 2 gives me -4. Okay, so what value, x minus 4, what value for x has to go in there to make it equal 0? 4. And how many carbons have to share that +4 charge or oxidation state? 1. And so that means that carbon has an oxidation state of +4. So carbon is equal to +4 and oxygen is equal to -2. Not the totals, right? We're talking about what's going on up here is our actual oxidation numbers. Oxidation number, oxidation state mean the same thing, right? We're talking about the same thing there, but we're looking not at our totals, right? This is just our workspace down here. This is our actual oxidation numbers.
What would you do if you had like?
What it means when we say carbon has an oxidation state of -4. Here's a carbon dioxide molecule. Right? You remember this? Lewis structures.
How about sentence?
Lewis structures. Okay, so oxygen is pulling on those electrons in the bonds closer to itself. Right? Oxygen's more electronegative than carbon. And so carbon is taking on, basically within each of those bonds, a partial positive, partial positive, partial positive, partial positive, right? In each of those charge. And so carbon's charge in that molecule is +4. It's not really +4, but it's kind of +4. You know what I'm saying? It's not a full-on charge. There's not a trading of electrons. They're sharing those electrons. But that also means that in each of those bonds, oxygen's got a partial negative, partial negative, partial negative, partial negative, right? So there's where oxygen's -2s come from, and that's carbon's +4, right? It just has to do with the electron distribution around that atom. Carbon has being electrons pulled away from it, so that's a +4, and each oxygen has 2 electrons coming towards it more, right?
So carbon's like taking the inner parts of the.
Like the bond, so the 2 electrons in each of those bonds, right?
Okay.
There's 2 electrons in each bond.
Yeah.
One from oxygen, one from carbon. But carbon's electron is being pulled closer to oxygen because oxygen's more electronegative.
Okay.
And so it's kind of taking on, now oxygen's kind of getting an extra electron from that bond in each place. Okay, yeah.
What's that little symbol you drew?
Okay, this means partial. It's like a Greek letter. I think it means delta. It's like a lowercase delta. Partial positive, partial negative. Right?
What? Oh, it does.
No.
Let's see. Let's try this one. N2O3. N2O3.
By ourselves?
I don't care. Do you want to do it by yourself?
Yes.
Okay.
Do it.
You got it.
There's a lot of examples of this.
Yeah, the next slide we'll do a lot of them. We can do some together. So oxygen was a -2. There's 3 of them, and so the nitrogen has to share that +6. So what would happen if you had a number here that was not divisible by that number?
You would have to.
Yeah, I'm going to try to avoid that. Okay? It's not really realistic that we would take on a fractional oxidation number, but sometimes the book does that, which I don't love. So just go with what the math says, but I will try to avoid questions like that.
So what should we do? Like just put.
Okay, this first one here, we're going to break it into kind of, look, here is a metal. Sorry, I think I clicked fast there, but this one's a metal, right? Potassium is a metal. Metals get to keep their own regular charge. Okay, then we go with chromium after that. Another way you could do it is to just split it, reverse it like this, and say you've got K plus 1 and you've got Cr2O7 minus 2, right? And find the oxidation states that way. You could split them or you could just treat them like a metal. Okay, that's going to be my preference here. Let me write it a little bit bigger off to the side. K2Cr2O7. Okay, the metal gets to keep its regular charge, but first we've got to take care of the oxygen, right? One of our big 3 is present, so -2. We want our totals down here to equal 0, so 2 times 7 is -14. We're always going to work, if you've got 3, work from the outside, then in. So make your middle one the one that gets adjusted last. Okay, outside in. So it's okay. The only other way we would see over here is a hydrogen over here, and that's gets third precedence of the big 3 anyway. So we would go work still outside in. So potassium is normally +1, that's a +2. So what number has to go there to make it?
2. No.
Well,
No, I thought.
6.
I'm with you. Okay. What number has to go? 2 plus 12. 12. And 2 chromiums have to share that.
Or 6.
I think it's 6, okay? Plus 6. Okay, so you can...
Oxidation levels we need to.
The only time I see you necessarily having to pull them is if you've got... Let's say you've got something like that, right? You've got 2 polyatomic ions that are kind of busy. We could pull those apart and do NH4 plus and SO4 minus 2 separate. You know what I'm saying? That might be the more applicable way to do that one.
So then you get rid of the 2 on the NH4?
Right, we would crisscross them reversed, and you would have NH4 plus and do the oxidation numbers there, and you would go SO4 minus 2 and do the oxidation numbers there. Yep. Okay.
That would be a case where you're trying to go to the charge.
That's right. Yep. Let's do the next one here. That has a charge with it.
Oh, neat.
Yeah.
All right, so CO3 minus 2. So we want our totals down in our workspace to equal minus 2, right?
Yes.
Oxygen is one of our big three, so we're going to go minus 2. That gives us minus 6. And so what number has to go there?
4.
No.
4.
Yes, 4. Sorry, I was saying no to 6. Only one carbon has to share that plus 4, so that means oxygen is minus 2 and carbon is plus 4. Okay, why don't you try the next 3? Oh, we didn't talk about one thing here. What if our big 3 is not present?
Then it goes to 0.
You
Right?
just guess.
No. One of our big 3 is not present. The most electronegative keeps its charge. So the one on the right gets to keep its regular charge. So chlorine would be -1, and then phosphorus has to adjust from there. So without the big 3, the element on the right gets to keep its regular charge. You might want to write that down on your rules slide. I didn't put that one in there.
No.
Wait, can you say it again?
Yep. I'll write it out here so you guys can put it on there. So if fluorine, oxygen, or hydrogen aren't present, the most electronegative element keeps its charge.
So, and we use our ionic periodic table for the
We just speak French out.
we.
Yeah, we talked about.
All right, this is what I had for each of those 3. Without the big 3 present, right, chlorine got to keep its regular charge, which is -1. Phosphorus had to adjust, right? +5 is not a normal charge for phosphorus, right? Phosphorus is normally -3. So the fact that it's at a +5 oxidation state means that it's like uncomfortable in that compound, right? Yeah, well, I mean, nothing to write home about, I don't think, but, you know. We talked about assigning oxidation states. Now we're going to talk about what are called redox reactions. And we said in redox reactions, there is a transfer of electrons that happens. So in a redox reaction, that means at least one element changes its oxidation state. Okay, at least one element changes its oxidation state. That's how we know it has been a redox reaction. Okay, so there's been some transfer of electrons. They may form ions, whatever it might be. These are 2 terms we need to know. Oxidation and reduction.
Oil rig.
Yep, I use this acronym oil rig, and we'll talk about that here in just a second. But oxidation means we have a loss of electrons. We have a loss of electrons. We've got to really train our brain to remember what a loss of electrons would look like. Okay? And then reduction means we have a gain of electrons. So our oxidation number becomes more negative. Okay? We will use the acronym oil rig. OILRIG. And I use oxidation is loss. Reduction is gain. Right? And I even write at the end of electrons so I remember. Okay, oxidation is loss of electrons. Reduction is gain of electrons. Okay, and so we're going to see what that means here in just a second. Okay, the secondary part of this is that if I have an element that has been oxidized, that is also what's called the reducing agent, right? It's what caused the other thing to be reduced. I'm not super concerned about what the agent is, right? We're more concerned about what happened to the actual element itself, but I think your book asks you some questions about the agents. So those are on the next page as well. But if it is oxidized, it is what is causing the reducing, right? So it's a reducing agent. If it's reduced, it's the oxidizing agent. You can't have one without the other. So it can't be like an element in the reaction was oxidized, but nothing was reduced, right? That can't be the case because if oxidizing is a loss of electrons, well, where do those electrons go? Right? They had to go somewhere. Something had to accept them. So we can't have a reaction in which an element was oxidized and nothing was reduced. Right? That's not possible. So you have to have both. It's either we've got a redox reaction or we don't. Right? Okay, yeah. If something is the oxidizing agent, it was the one that was accepting the electrons. So if it is reduced, it is the oxidizing agent. If it is oxidized, it is the reducing agent. So they just like partner, okay? If it was oxidized, it lost electrons, which means it caused something else to gain electrons. I don't know. I'm not too concerned about the agent itself, but we're going to do some practice just assigning that so we know for sure. Okay? Which of the following are oxidation reduction reactions? So if something happens and nothing is oxidized or reduced, you just write not a redox reaction. Right? It didn't have any reduction or oxidation. But let's look at the first one. Okay. We assign our rules for oxidation numbers to every element. Okay, so zinc by itself has an oxidation number of 0. Good, that's rule number 1. HCl, okay, hydrogen is one of our big 3. It has an oxidation number of +1, which means chlorine then has to be -1, right? So let's move over to the other side. ZnCl2, does it have one of our big 3? No. So chlorine gets to keep its regular charge, -1. That means that's -2, which means zinc has to be what? +2. And then hydrogen by itself, H2, has an oxidation number of?
+1.
Nope. Nope. 0, right? That's rule number 1. Rule number 1, right? You forget about that. If it's by itself, it has an oxidation number of 0. So now we look at elements individually. So zinc went from 0 to +2. So what happened with its electrons? What did it do?
It gained electrons.
Did it?
No, it lost electrons.
It lost electrons, right? It lost electrons, okay? What happened to hydrogen? It went from +1 to 0. It gained an electron. And what about chlorine? What happened to it? It went -1 to -1, so it didn't do anything, that's what the case should be, right? We can't have 2 things that were oxidized and one that was reduced. So what we would say here is that zinc was what? Oxidation is loss, reduction is gain, right? And I even have to still write out oil rig, so I remember. Oxidation is lost.
Oxidation and an O in loss.
Right?
No, I'm gonna remember forever.
Okay. Lost electrons means this was oxidized.
Okay.
And this was reduced.
So you have to go by
Each element, right? We look at each element.
Wait, but since zinc lost 2 and H only gained 1, isn't that a little awkward?
Well, we had a mole ratio there of 2.
So
Yeah, does
Oh,
that
okay.
not affect
Yep.
the...
It doesn't. Okay, the oxidation number is not really affected by the mole ratio. The mole ratio will still account for the number of electrons there, but that's a good question. The mole ratio will take care of itself. Right.
Okay, wait. So zinc is like giving 2 electrons to the product
It's
side?
putting 2 out in the atmosphere, right? Let's just pretend that. That's not really what's happening. But let's say it gives away 2. Hydrogen picked both of them up because 2 hydrogens from this became 2 hydrogens that were neutral.
Okay, so you have to look at the mole ratio when you're doing...
I don't think you need to look at mole ratio when you're doing oxidation numbers.
You just trust it.
Yeah,
Wait.
it works out.
Just trust the
Trust your gut.
All right, here. What's the oxidizing agent and reducing agent?
The oxidation agent is
The oxidizing agent was H.
Right.
The reducing
And this is the
agent-
reducing.
So it's
Oh.
just the opposite.
Yeah, it's the opposite. Right. I'm not really concerned about the agents, but
Everything
it
is
will
opposite.
ask.
Everything is
You
wrong.
add 2, you lose them.
There's CR207 -2. So we want our totals down here to add up to -2. It has one of our big 3, so oxygen's -2, -14, which means this needs to be
+7.
12. No.
+6.
Yep, because we want them to add up to -2. We don't want them to add up to 0. So that means chromium is +6. Right, on the next one, OH minus, we want them to add up to -1. Oxygen is a -2, hydrogen is a +1. Do we agree on that one?
Wait, but both of them are part of the big 3.
Yeah, oxygen gets it first.
Okay.
And if I have oxygen, which is -2, and there's one of them, that's -2. So what number has to go there? +1, and so that goes to hydrogen.
Okay.
Then I come over to the other side, CrO4 minus 2, so -2, -2, -8. Chromium has to be +6, good. And then on my last one here, oxygen is -2, -2. Hydrogen has to add up to +2, so each hydrogen has to be +1. So now I'm going to look at my elements and see what happened.
Nothing.
Yeah, chromium went from +6 to +6. Oxygen went -2 to -2. And it's -2 in both places that it is. And hydrogen's +1 to +1. So we just write not a redox reaction.
All that for nothing.
Yeah.
So